Hi, I'm Cyril Thomas. Currently, I'm pursuing MCA at Marian College Kuttikkanam, Autonomous. Today, I'm going to explain garbage collection and memory management using a graph theory perspective. Whenever we run a program, memory is continuously allocated and freed. Instead of managing memory manually, modern languages automatically clean unused memory using something called garbage collection. Let's start with the graph model. We think We can think of objects in memory as nodes in a directed graph. References between objects acts as directed edges. There are special nodes called roots, such as global variables and stack variables, which serve as starting points. So essentially, memory at runtime is a directed graph where objects are connected to references. Garbage collection is fundamentally a reachability program. The system starts at the root node and performs a graph traversal, usually depth first search or breadth first search. All objects reachable from the roots are considered live. Any object that cannot be reached is considered garbage and can be safely removed. So mathematically, garbage collection is just identifying unreachable nodes in a directed graph. To visualize this, imagine a city hall. City hall represents the root, roads represent references, buildings represent objects. If a building is connected to city hall through roads, it is active. If it has no path to city hall, it is abandoned and can be demolished. That's exactly how garbage collection works. There are two classic garbage collection techniques. First one is mark and sweep. The system traverses from the roots, marks reachable one nodes, and then sweeps away unmarked ones. Second is reference counting. Each object tracks how many references point to it. If the count becomes zero, it is immediately deleted. However, reference counting has a problem, cycles. If two objects reference each other but are not reachable from the roots, they remain in memory unless special cycle detection is used. A major issue with traditional garbage collection is something called stop the world process. During collection, the program execution is completely halted. In small programs, this may not matter, but in interactive applications, even small pauses can cause visible lag. So, modern systems try to reduce or eliminate these freezes. To solve this, modern garbage collectors use incremental traversal. Instead of scanning the entire graph at once, they process small parts over time. This work is interleaved with normal program execution. A common method is tricolor marking, where objects are classified as white, gray, or black to maintain correctness during traversal. Now, garbage collection becomes not just a graph problem, but also a scheduling and optimization problem. In advanced systems, memory management is treated as a dynamic graph problem. The graph consistently changes as new objects are created and references change. Modern optimizations reduce peak memory usage and significantly improve performance. This shows how graph theory directly impacts real-world system efficiency. In real-world engines like JavaScript runtimes, incremental garbage collection keeps application responsive. The system must balance two competing goals: maximize memory efficiency and minimize post time. This balancing act is essentially an operations research optimization challenge. To conclude, garbage collection is fundamentally a graph reachability problem. By modeling memory as a directed graph, we apply traversal, cycle detection, and optimization techniques. Modern systems improve performance using incremental and concurrent strategies. Understanding this perspective helps us see what truly happens behind the scenes when our program runs. Thank you.